So hello everybody. Today I will be presenting our newly developed fiber-tip spintronic terahertz emitters. But before I begin, I would like to start and to say thank you to the organizers here, so Romain, Tobias, and also Suki. Thank you very much. And as well, I would like to use this opportunity to express my gratitude to all the many people here that supported me in this research. And many of them are here today. So it's from Mainz, there's Matthias, there's Martin and Gerhard. We have, again, from Berlin, Tobias and Tom. From France, here today is Matthias. There's Nicolas, there's Jeffrey, also Pierre, as well as from our institute, Felix. So I don't know if I can transmit it to you right now, but it really means a lot to me. So thank you for all the support. Okay, so I guess in the meanwhile, everybody of you knows this image here already. And the most important part is this fiber sticking out here in the middle. And the idea we had in mind is that we wanted to try if it works to deposit the spintronic terahertz emitter directly on this fiber tip. And to provide you with a better intuition about the dimensions at play here, you see an SEM image, and this SEM image shows that the outer diameter of this fiber is really just 125 micrometers. And if we zoom in even a bit more, we see that in this case we use a polarization maintaining single mode fiber. We see that the pump light itself will be guided only within the core, and the core has a diameter of roughly 10 micrometers here. And later on I will show you one application we did where this core size or the core diameter is the crucial parameter for the resolution. Okay, so today I'd like to answer two main questions. The first question is it possible to realize such fiber-tip spintronic terahertz emitters? And the second, if so, what are possible applications? At this point, I would like to say that one question I don't answer today is how an STE works, so how the fiber-tip STE works, because I feel there has been many excellent presentations already, and I don't want to repeat here. So in general, the fabrication process, we can classify it into 4 different processes. So the first process is that we glue the fiber inside the ferrule. Then it is followed by a polishing, a cleaning, as well as the sputtering deposition. And within the next 6 to 8 minutes, I'd like to just guide you through all these processes here, step by step, and just explain you how we did it. But even before we start with the fabrication, we need to decide on the design of the STE, of the fiber-tip STEs. And the cool thing is that we can choose from a variety of different parameters. So for example, there are many standard glass fibers available, so based on silicon oxide, and they are doped with different materials. But there are also some nice crystalline sapphire fibers we can use. So they have also some kind of flexibility, and in this case, we can make sure that it's kind of like a sapphire wafer in the end. Another parameter we can choose is the core size. So we have a core size of 10 micrometers, but we also increased it to 100 micrometers or even up to 425 micrometers. And it just depends on the application you want to use. So sometimes the 10 micrometers is better, and sometimes the 425 micrometers. Besides that, there are 2 different ferrule materials available online. So there are either the ceramic ferrules or stainless steel ferrules you can buy. And last but not least, we can decide on the different connector type we would like to have for this fiber-tip STE. So at the beginning, we started with the version you see here on top. So it's a bare fiber. And the idea was there that we deposited the STE on the end facet here of this bare fiber. Then we started to do this pigtail design here. So we have a ferrule, and the fiber is held by this ferrule, so it makes the handling a bit easier. But we still have this fiber sticking out on the other hand that we can splice it to pump fiber. And then we realized that actually it also works quite well if we just use such a FCPC junction and we polish it on both sides, because the reflection losses to the pump fiber, they are more or less negligible. So for everything I show you right now, we use this FCPC design. And the first thing what we need to do is that we need to insert the fiber into the ferrule. And here we need to make sure that, especially on this end here, where there's a conical opening, that the fiber is really centralized in the middle. But once we have done that, we can place some glue and we can harden the glue using some UV light. The next step is then our polishing, and here I can just show you a short video. On the left side, so this is the polishing machine we have, and we polish the end facet now via a sequence of polishing steps. And mainly, maybe at this point here, because I thanked so many people at the beginning, I should also thank this polishing machine here, because in the early beginning, our great master student Felix and I, we were spending days and maybe even weeks just polishing everything by hand. So in the meanwhile, we are quite happy that we have this polishing machine and that we can especially reproduce the surface quality. And how is it done? So we start with the polishing paper with a grit size of 6 micrometers. So here you see there's quite the surface is quite rough, but we get rid of all the glue. And then the smaller the grit size of the polishing paper, the better the quality gets. And if we use final polishing paper in the end with a grit size of only 20 nanometers, we can really guarantee that we have a wafer-like surface quality of our fiber tip. And here to just prove it, that's really wafer-like, we took an SEM image, and you see in the zoom on the right side that the surface is completely smooth. One thing, however, that was also really important is that we need to have an extensive cleaning. And here on the left side, you see a microscopy image of one of our first fiber tip STEs we ever produced. And even though we had a cleaning process in place already, you can see that the surface quality, it's quite greasy and it doesn't look good. So we spent quite some time in optimizing this cleaning procedure. And here on the right side, in this case, it's an SEM image. You see that now we are able to control the surface quality, and we get always these nice surfaces here. Okay, so once this is done, now we have polished everything. We cleaned it. We are ready to put it into a sputtering chamber. And the idea is that maybe you can see it here on the image on the right side. We produce some smaller boxes, and we can just put those ferrules into these boxes, and they are held in place. And then we have in one sputtering chamber here, you see we have 4 boxes. So in this case, we produced 36 fiber tip STEs. And we decided to go for the well-known tri-layer design. So it consists of 2 nanometers of tungsten, 1.8 nanometers of iron cobalt boron, and 2 nanometers of platinum on top. And in terms of sputtering deposition, we did an RF sputtering deposition technique. So we applied an AC field between the cathode and the anode here at the bottom. Okay, so once this is done, we are now ready to integrate everything into our existing setup. And here again, a short video. You see the fiber tip STE here now in the middle, and we have this nice FCPC connection. And we also built this nice external magnet where you can rotate and optimize the polarization or even control it. And to summarize, everything is now fully fiber coupled. There's the seamless integration into any existing setup. And also one really nice feature is that we can exchange it within a minute. And especially if you think about that you would like to try out many different designs, or in our case right now we are investing a lot of time into the material destruction threshold. Due to the wave guiding within the fiber, it is guaranteed that we always have the same initial experimental conditions, and we exactly know how the pump mode field looks like, so there's no deviation in that. So then it's really cool that we can just, for example, burn 10 different samples within 1 hour just to get more information about the destruction threshold. Okay, here's the final proof that it works. So in the end, we see that our fiber tip STEs, they exhibit the same performance as conventional free space STEs. And in our laboratory, we use an erbium-doped fiber laser with an average pump power of 150 milliwatt. We have 100 megahertz repetition rate and 70 femtoseconds full width half maximum pulse duration. We achieved the dynamic range of 42 dB. And as you can see, we are also able to clearly resolve those water vapor absorption lines. So the second big question is, what are the possible applications? And one possible application that it just appears naturally if we use single mode fibers is a terahertz near-field imaging system. And the idea is pretty simple. You can see it here. So the system consists of one erbium-doped fiber laser. We split it 50-50. one arm goes through the delay and to the fiber tip STE, the other arm gets amplified as well and goes to the PCA detector, and we collect the terahertz radiation using 2 parabolic mirrors. And the idea of the measurement is quite simple. So we take a resolution target, a metal mask, and we bring it into really close vicinity of the fiber tip. And now by moving it into X and Y direction, we can do some imaging. And if we do that in one dimension, it's basically a knife edge measurement. So we have one metal plate and we move it in that direction over the fiber. And you can see the results here. You see that if we use a core diameter of 425 micrometers, we don't get a good resolution. So we are about like 380 micrometers. But as we would expect, like the smaller the core diameter, the better our resolution gets. And in this case, because we use those single mode fibers, we got a resolution of 30 micrometers here. And here I would also like to mention that we didn't push for the maximum resolution here. So we just wanted to show that in principle it works. And for example, the metal plate we used here was quite thick. So I think the actual resolution is even lower. So it should be more or less on the scale of the pump mode field diameter we use. Okay, so the cool stuff happens in 2 dimensions. So now we can do some imaging. And here again, for proof of concept, we took 2 metal strips. And they have a width of 77.5 micrometers. And they are 122.5 micrometers apart. And what you can see here on the left side is that if you use a fiber with a core diameter of 250 micrometers, we cannot resolve anything. But if you reduce it down to, let's say, 100 micrometers, it starts to become visible a bit. And if we use the single mode fiber here on the right side, we can clearly resolve everything. So this was, for us, just a nice proof of concept that it would work. And I think the technique is quite similar to what Markus presented just 30 minutes ago, just fiber coupled. Okay, another thing is that we did a proof of concept in terms of layer thickness determination. And at our institute at Fraunhofer ITWM, we have a lot of expertise in building these transceiver modules to make layer thickness determination measurements. And you see we have a transceiver module here. Everything is fiber coupled. We put the fiber tip STE inside here. Then we have an optic that focuses the terahertz beam to the sample under test. In this case, we just took a Tesa strip on metal, and then it is collected again and measured via PCA. And in our normal transceiver modules, we have a PCA emitter here as well, and now we just replaced it. And the idea of the measurement is simulated here. So we have a terahertz pulse, and we get a reflection at the first interface, and a second reflection at the last interface. And then we can simulate this waveform here, and in principle, we would also be able to make a multi-layer thickness measurement. So if you think about a car body painting, there you have 3 to 4 layers of different coating. So with the PCAs, we are able to really resolve that. And the idea is now that we make an experiment. We take this measured waveform here, and we compare it to the simulation. And then we tweak the simulation, and we fit the simulation to the experiment. And by that, we can extract the information, the material information we are interested in. And in this case, because we know the refractive index of the material, we can determine the layer thickness. And here, I just showed that we used different layers of Tesa strips. But on the y-axis, we have the single layer thickness. And what you see is that we basically measure the same thickness for the Tesa layer, so this makes a lot of sense. And it was a nice proof of concept. Thinking a bit more visionary, and this is actually the part I'm really excited about, even though I know that we need to be patient a lot and maybe wait for 10 or 20 years. But still, the idea is quite cool. So imagine we take one glass fiber, and on the tip of this glass fiber, we deposit a STE. But now we take a second glass fiber next to it, or even a dual core fiber would also work. And now rather than putting STE on top, we put an STD, so a spintronic terahertz detector on top of it. And when we do that, we have like a flexible endoscope to make some endoscopic measurements at destinations where we wouldn't be able to get otherwise. So you can just see here a small cartoon about it. And in principle, with that, we could do some near-field imaging in hidden destinations. And one cool thing would be that if we get rid of the need of the external magnet for that. So we took at least this intermediate step already, and we built some magnetic bias-free fiber tip STEs. And how did we do it? We exchanged the iron cobalt boron layer by a tri-layer consisting of iron cobalt and terbium cobalt. And in addition to that, during the sputtering process, we induced an anisotropy by applying a strong magnetic field. And here's the result. So you see, again, it works. So I'm happy that at least like one small step towards this endoscopic measurement is done. I would also like to talk about one limiting factor, and this is the optical damage threshold. And what we see is that if we increase the average power too much, that after the experiment we see those dark spots appearing here, and also we see that, that we don't see any terahertz signal anymore. And at the beginning we thought that is something just related to our way of producing the fiber tip STEs, but in the meanwhile we realized that actually many people have a similar, see a similar problem. And it has been mentioned in some sentences in the publications. So for example here, Nandi et al. Or Vogel et al. But also from discussions we see that Melanie has those issues. Xiao Jung also sees it in the SNOM measurements due to the light field enhancement. Matthias told me that he sees it in the photo mixing. So this seems to be a problem many people have. And because of that, we have a lot of interest in at least characterize it better. And we are currently about to submit a publication about it. And what I can share from that already are just two very simple measurements. So we measured the infrared transmittance, and we see that over a second to minute timescale, so here 120 minutes, we see that the infrared transmittance just increases. And also we see that there's a clear terahertz hysteresis when we do those experiments. So it's clear that it's damaged, and from my point of view, it's also clear that it is a heat-based problem, and it is a problem that only happens in the high repetition rate regime, so in above, let's say, 400 kilohertz. And so we are heating up the material and then we destroy it. But this is very important because in the literature so far, there are only articles about this low repetition rate regime below 400 kilohertz and nothing above. And in our case, we see an optical power density threshold of below 2 kilowatt per square centimeter. Okay, so with this slide, I would like to conclude. So where are we today? Today, we have the simple prototyping tool to fabricate a variety of different samples, and it is guaranteed that we have always the same initial conditions due to the waveguiding. And also, especially if you think about potential industrial applications, we are able to build fully fiber-coupled systems in the meanwhile. Talking about the future, I say that quite visionary, but maybe I will turn 30 in actually less than 2 hours. So I have a lot of time in my lifetime to maybe make it possible that at one point in time we will see it. And secondly, if you think about integrated terahertz photonics, this also might be a cool application, especially the buzzword ST on a chip, I think sounds cool. Okay, thank you very much. If you want to have more information, you can just scan the QR code or ask me any questions. Thank you.